Welcome to Module 1 and the Introduction to the Theory of Computation. In this video, we're going to talk about the theory of computation and mathematical preliminaries and notation. So let's get started. In the 1930s, before there were computers, Alan Turing studied an abstract machine that had all the capabilities of today's computers. So let's think about that for a second. In 1930, Alan Turing studied an abstract machine that had all the capabilities of today's computers. It was called the Turing machine. We are going to learn about the Turing machine in this course. His goal was to describe precisely the boundary between what a computing machine could do and what it could not do. And his conclusions not only apply to the abstract Turing machines, which we're going to learn about in this class, but also to today's real machines. So the theory of computation in computer science includes the study of language definition, pattern recognition, and the capabilities and limitations of algorithmic computation. We're going to analyze the complexity of problems and their solutions. This is a theory class, but we are going to do a lot of practical work with abstract models, and it's not just going to be, we will later talk about limitations of algorithmic computation and stuff like that. But along the way, in studying, we are going to be drawing abstract models of computers and studying languages and doing some work with that. And it's actually, if this class can be very fun and interesting, working with these abstract models and studying these languages. And why would you do that? Because it helps us understand the general nature of computer science. All right, so here are the parts of this class. We have automata theory, formal languages, and we have grammars. And what we're studying is what can be done in computers by principle in computers. And the thing is, we're going to start with very simple things and then move on to much more complex situations. So let's get some definitions out of the way first. What is meant by an automata? So an automata is plural for automaton. An automata is a model of the hardware of a computer. So we're going to be drawing automata, and we're going to be studying different languages. They're classified, if you look at the last bullet here, it says they're often classified by the class of language they accept. So what does an automata do? Well, we're going to be using state diagrams to draw automata. They accept input, they produce output, they could potentially have temporary storage, and they make decisions about transforming the input to the output. In automata, there are transducers and there are acceptors. In the beginning, we will just be using acceptors. That means they either accept or do not accept, but transducers can also produce and transform the output. A formal language is an abstraction of the general characteristics of a programming language. Grammars are used to generate languages. And automata theory is mathematical models of computation and the study of abstract computing devices. And that's what we will be doing in this class. I have here the hierarchy of languages and automata. If you take a look at the top row there, we have a Turing machine and recursively enumerable languages. We will not be starting there. We will be starting at the bottom with regular languages and DFAs and NFAs, and then move up through more complicated languages and more complicated automata. So this might not make a lot of sense right now, but as we go through this course, we will start at the beginning with regular languages, move on to context-free languages, context-sensitive languages, and each time it becomes more complicated, the grammars become more complicated until we get up to the Turing machine and recursively enumerable languages. And I will bring this back. We actually have a whole module on the hierarchy of languages. But before that, let's just do some mathematical preliminaries and notation, just to make sure that we have a good understanding of some of this preliminary information. So let's define what is a set. A set is a collection of elements. The only thing important about a set is that it has membership. This is set notation. You use curly braces, and the integers 0, 1, and 2 are members of this set called S. Here's some more notation. You could say you have set S, and X is an element of S. Using this notation. To say X is not an element of S, then you use this type of notation. This such that, so you wanted to say S is the set of I such that I is greater than 0 and I is even. So you need to, we're just getting this notation out to make sure that later when I give you questions and problems and you have some background on this notation. Let's make sure we have an understanding of union, intersection, and difference. So if you have two sets, S1 and S2, then that means that any elements that are in S1 or in S2, that is the union. Intersection means that the element must be in S1 and also in S2. And difference means that if it is in S1, then the element is not in S2. The universal set. So the universal set is the set of all possible elements. So if you have S complement is shown with this notation. You could either have S with a little c next to it, or you could have S with a line over it to indicate it's the complement of S. So if X is a member of the universe of X complement, so if you take a look at this notation, this notation says X such that X is a member of the universe, the universal set of S complement. So if X is in S complement, which is every possible element that could be in the complement of S, then X cannot also be in the set S. The empty set or the null set, that is the set of nothing. So if you union S with the empty set, you still have S. If you subtract the empty set from S, you still have S. The complement of the empty set is the universal set. So just, I know this all seems very straightforward, but we just want to review and make sure. And if you do have any questions on this, I have slides posted, a video, notes, and this is all in chapter 1 of your textbook. The complement of S is S. That's the complement of the complement. De Morgan's law, hopefully you guys have studied De Morgan's law and you are familiar with it, that if you take the union of S1 and S2 and you take the complement of that, then that would equal the complement of S1 intersecting with the complement of S2. Also, if you intersect S1 and S2 and take that complement, that would equal the complement of S1 union with the complement of S2. And I have these diagrams here to make it more clear. Also, you can see here, you can either do complement by putting a little line above, or you can show the complement with that little, if you guys can see it on the slides, the little C. Subset. So this is notation for a subset. This is saying that S1 is a subset of S. A proper subset, that means that S contains an element not in S1. Disjoint, so as long as you get the terms disjoint, if you intersect S1 with S2, then you get the empty set. That means that there are no members in S1 that are also in S2. This notation means the number of elements in a set. The power set, the set of all subsets of S is denoted by the power set, which is also 2 to the S. So here's an example of the power set. Keep in mind that we need to keep, so there's a couple things here that's important. You can see the subsets of S are sets themselves. See the notation? The power set of S includes the empty set, the set that contains A, the set contains B, the set that contains C, the set that contains A and B, and etc. So keep in mind that a power set is a subset of sets. So you have to have that notation correct, that that's not just the set. If you removed these extra curly braces around A, B, then you would have a set, right? But these are all sets. That's the set of A, the set that contains B, the set that contains C, the set that contains A and B, etc. Okay, the size of the power set is the same as 2 to the S is the same size as 2 to the size of the power set. Cartesian product. This is a very simple Cartesian product. So if A contains 1, 2, and 3, and B contains 1, 2, then you just put each element with the element in the other set. Notice this notation. You're not making sets. You are making one set that is the Cartesian product. Where if we go back here, if you go back and look at the other slide, that was a set of subsets. So the notation here, this is one set that is the Cartesian product of two sets. It is not a bunch of subsets. So that's why we're using parentheses here and not using a bunch of curly braces. All right, functions. Each element of the domain in a function has exactly one associate element in the range. So you have to, you hopefully have all studied functions and understand what a function is. If functions are represented as ordered pairs, and if x1 is an element in the domain and y1 is an element in the range, x1 can occur at most once. Otherwise, it's not a function, it is a relation. So you need to understand the difference between functions and relations. And okay, graphs. Graphs are a construct consisting of two finite sets. You have your set of vertices and you have a set of edges. And we're going to talk about tuples. So a pair is a two-tuple. So each edge is a pair of vertices, right? You have an edge that goes from one vertice to another vertice, and that the term tuple means that you have two elements to define that. So we're going to be doing 5 tuples and 4 tuples, so you need to understand the term tuple. Okay, a sequence of edges is said to be a walk. A tree is a directed graph, and there's one path from the root to every other vertex. So just some preliminary things about graphs and trees. We will be drawing graphs, and we will, but just as long as you guys understand these terminology, tuples and edges and directed edges and vertices and all of that,